Hey guys, welcome to the 10th episode of Short Bits by Shorty. This one's about antipsychotic agents. Just remember, know the concepts, not all the examples. Know the concepts and the prototypes, and you should be able, after this video, to answer hopefully any question he throws at you. Also, just like the last video, I'm going to put an example in the cloud. Please do not know anything in the cloud. Those are just examples. So yeah, with that, let's begin. Okay, so your first class we're going to talk about are your tricyclics. These are linear combinations of two benzene rings of isosteres surrounding 6 or 7 membered rings. So in English, this means that these are straight up, that means they're straight in a line, combinations of two benzene rings, 1, 2, 1, 2, or benzene rings with combinations that still produce or changes that still produce activity. Remember that isosteres are related compounds or compounds with just a few changes that still produce the same activity as the original compound. For example, an isostere of this benzene right here would be changing one of the carbons to a sulfur, or an isostere of this benzene would be changing one of the carbons to this is an oxygen. So basically any change in a molecule that still produces the same activity as the original molecule is an isostere. So linear combinations of two benzene rings, benzene ring 1 or 2, surrounding 6 or 7 membered ring. So here's your 6-membered ring, here's your 7-membered ring, and these are both examples of tricyclic antipsychotic scaffolds. Remember that central rings that are less than 6 or greater than 7 members, so here's 6, here's 7, lead to inactive compounds. So if he gives you 2 sets of rings, if he gives you 2 sets of rings, this one's a 5-membered ring, this is a 6-membered ring, which one would you expect to be inactive and why? So the left one is inactive because it has a central ring of less than 6. So remember, look at the central ring. If it's less than 6 or greater than 7 members, it's inactive. And this one's active because it contains 6 members. Okay, so your first subclass of your tricyclics are your phenothiazines. So the prototype, make sure you know this one is not in a cloud. It's chlorpromazine, or abbreviated CPZ. Here's the structure. So if I ask you why is this inactive? Is this active or inactive considering the central ring? What would you say? Active or inactive? This is active. Well, obviously it's a drug, but active. It's because it has a 6-membered ring in the middle. Remember, less than 6 or greater than 7-membered rings in the middle are inactive. So the CPZI, which is the chlorpromazine index, is a measure of relative potency of a drug compared to CPZ. So by default, CPZ, or chlorpromazine, is set at a CPZI of 1. So an agent with a CPZI of 2 is more potent or less potent than CPZ. It's more potent, specifically twice as potent, because it has a greater CPZI than chlorpromazine. Likewise, a CPZI of 0.5 is half as potent. Okay, so now we're going to go over the SAR, not Sapphire, but SAR. Ooh, review. What is the difference between SAR and Sapphire? Sapphire refers to the affinity of a molecule. structure affinity relationship. SAR refers to the structure activity relationship. And activity is not necessarily related to affinity. Remember that. Okay, anyways, here's the SAR of your phenothiazines. Let's see. So the SAR depends on 3 parts. I highlighted it in yellow for you. Your ring system, your side chain, and your terminal amine. So those are your 3 basic parts of your SAR of your phenothiazines. So I'll go over each one separately. Actually, I'll go over everything on the right first, and then I'll go over everything in the bottom. The rings, everything yellow. Since the right one's more self-explanatory or more easily explainable. So your X over here, sulfur is optimal, sulfur is optimal, not optional, optimal. Y over here, has to be optimal, it has to be a nitrogen or an sp2 hybridized carbon. Ooh, review from the last video. What are examples of sp2 hybridized carbon groups? You got your C double bond C, C double bond O, C double bond N, C double bond S. Those are examples. Make sure you know those in case you have to draw them. So Y can be a nitrogen, or a C double bond C, C double bond O, C double bond N, or C double bond S to be optimal. At your 2 position, which is right here, it has to be an electron withdrawing group. Ooh, review again. What are examples of your electron withdrawing groups? Let's see. Remember, knock off Burkle from the last video. Knock off Burkle. You like these throwbacks to the last video? You gotta know things. So knock off Burkle. NO2 is more electron withdrawing than CF3. CF3 is more electron withdrawing than BR. BR is more electron withdrawing than CL. And for your anxiolytics, your affinity goes the same way. NO2 has a greater affinity than CF3. CF3 has a greater affinity than BR. BR has a greater affinity than CL. Okay, so be sure to put one of those groups at your 2 position, which is over here, to get optimal antipsychotic activity. At the 3 position, which is up top over here, you can have, usually it's a hydrogen, but you can have electron withdrawing groups. Caveat, don't put electron withdrawing groups at both the 2 and the 3 position. So you can't put an NO2 at the 3 and an NO2 at the same time. It has to be either or, the 2 or the 3. The R1 and the R2 groups both have to be optimal, both have to be present. So any substituent at the R1 and R2 group is optimal. Both of them are optimal. Leaving them unbranched is optimal. So let's see. R1 cannot be that. That's your branching. You have a carbon here, carbon here, carbon here, 3 carbons. R2 cannot be, I don't know, branching. Hold on, that's not branched. Just kidding, ignore that. Branched. That's another branch. So you have carbon 1, carbon 2, carbon 3, carbon 4. So no branching is optimal. Let's see. And at your amine, which is over here, a secondary amine is less potent than a tertiary amine, which is less potent than a piperidine. I don't know how you pronounce it. And the piperidine is less potent than your piperazine. So, in case you forgot what secondary means, and tertiary and piperidine and piperazine mean, I'm going to draw it out for you. So a secondary amine is an amine with only 2 groups attached. So over here, I'm just drawing this carbon attachment over here. And you only have one R1 group. Tertiary amines. This is a tertiary amine. I'm lazy. This is a tertiary amine because it has 1, 2, 3 attachments. That's tertiary. Secondary only has 2 attachments. 1, 2. Your piperidine is your process. It's like a 6-carbon sugar, except one of your carbons is a nitrogen. And you and your piperazine is like your piperidine, except you have a nitrogen at the other end. Cool. So that's... Yep. Okay. Let's see. What else do I need to go over? Okay. So that's all the right side. Now, details on the bottom in the yellow. So the ring system is not planar, but it's actually V-shaped. If you look at it 3-dimensionally, it's actually V-shaped and not planar. If you have a planar compound, you do not get activity. So to illustrate, if you want to delete activity by creating a planar ring system, you can easily do that by creating a 5-membered ring in the middle, which also goes against the rule of active cyclotic rings being 6 or 7-membered rings. So this is not active for 2 reasons. One, because it's a less than 6-membered ring, and it's planar. So this one's planar. Don't memorize this. It's in the cloud. Okay, what's next? So 5-membered rings produce planar compounds. Well, 5-membered rings in the middle. Yeah, 5-membered. Or 5-membered in the middle. Why don't you just meet me in the middle? I'm done. Okay, side chain. 3-atom side chain is optimal. Branching or shortening can unmask the antihistaminic or anticholinergic effects. Okay, so let's do. Okay, so 3-atom side chains. Yeah, okay. So 3-atom side chain is optimal. So looking back over... Wow, I didn't label that. Okay, so this is your side chain. So I said 3-atom side chains are optimal. So this is your side chain. So here's carbon 1, carbon 2, carbon 3. So that's 3 carbons. So that is optimal. So let's see. Why are 3 carbons optimal? Well, anything less produces an antihistamine. So here is, or more of an antihistaminic drug. So here's the general structure of antihistamines, which has phenyl group, aryl group here, a benzene ring here, a benzene ring here, carbon or a nitrogen here, X equals carbon or nitrogen, and you have a CH2, and forgot to write that. Hold on. Okay, so as I was saying, here's a phenyl ring, X, which can be carbon or nitrogen, CH2, and you can have 2 or 3. N means you can have this N corresponds to how many you can have. So CH2 2 means you have 2 CH2 groups. CH2 3 means you have 3 CH2 groups. And then your tertiary amine. Why can't antipsychotics produce antihistaminic effects? Well, if you look at the two structures, so you have your phenothiazine and then your antihistamine. If you looked at the really structurally related, you have a phenyl group, X over here, which can be carbon or nitrogen, Y over here, which has to be nitrogen to be optimal, and then you have a CH2, and then your N, your tertiary amine. So let's see. So if you, antipsychotics or especially phenothiazines can produce antihistaminic effects if you shorten the chain. For example, here's your phenothiazine. Or here's chlorpromazine. No, here's chlorpromazine. Sorry, I don't know my drugs. Oh crap. Oh crap. I forgot the chlorine here. My bad. There you go. Ooh. Okay. Anyways. Let's see. Well, that's a chlorpromazine analog. Okay, so if I gave you two structures, which one would you predict to be more antihistaminic? The left one or the right one? The left one is hypothesized to be more antihistaminic because it has only 2 carbon side chain, 2 carbon rather than 3 carbon. Remember, antihistaminics prefer 2 carbon side chains. But to get more antipsychotic activity, you need a 3 carbon side chain. So as I said before, let me write that down in case you were more antihistaminic. So left one's more antihistaminic because it has more of the antihistaminic 2 carbon side chain, 2 carbon rather than 3 carbon antipsychotic chain. And you can read about it up here where I said oh no, down here, just kidding. 3 carbon side chains are optimal because less than 3 produces more antihistaminic activity. Okay, so what if okay, let's go over here. What if I gave you 1, 2, 3, 4. That's 4 carbons. Tertiary amine. Okay, so what if I gave you a 4 carbon? If everything was the same, what if I gave you a 4 carbon? Would you have less or more antipsychotic activity? You'd have less antipsychotic activity. So, in general, less antipsychotic activity with shorter, longer side chains. So shorter or longer than 3 carbon atoms of a side chain result in less antipsychotic activity. Okay, what if I branch this baby? So let's see. Everything being the same. 1, 2, 3. So it's still a 3 atom 1, 2, 3 side chain. But what if I had branches? Will that decrease or increase antipsychotic activity? You would decrease it as well. So, decrease antipsychotic activity with shorter side chains, longer side. Oh, this is your brain. Shorter side chains, longer side chains, and branched side chains. Put that in blue for you. Okay. Let's see. So yeah, to summarize the side chain effect, 3 atom side chains are optimal because, well, of the antipsychotic activity. Anything less produces more antihistaminic and or anticholinergic activities. Anything more produces less antipsychotic activity. Any branching the side chain produces less antipsychotic activity. Okay, let's see. Next up is your terminal amine. So I'm referring to this amine right here. So remember that both R1, R2 have to be present, meaning it has to be producing a tertiary amine. If R1 and R2 are here and nitrogen is attached to this carbon, then you have 1, 2, 3 groups attached to nitrogen, so you have a tertiary amine. Whereas 2 groups attached to nitrogen over here, 1, 2 produce a secondary amine. So tertiary amines are optimal. Unbranching them is also optimal. What else do I have? What else do I have for you down here? Oh, they have to be basic. Let's see, which I will go over right now. Oh, by the way, these are all examples. I'm too lazy to put them in the cloud. Actually, I'll put them in the cloud because there's some functional groups. So these are in the cloud. Remember, clouds are examples. Don't memorize them. I'm just using to illustrate my points. Or Dr. Glennon's points. Not mine. Cool. Bet. Let's see. Okay. So... Okay, so everything else being equal, you have 3 molecules. Well, everything else being equal means like everything, the scaffold is the same, the 3 carbon chain is the same. The only thing we're changing right here is the nitrogen, the nitrogen part. So here we have a tertiary amine, secondary amine, and a quaternary amine with a positive charge. Quaternary amines have positive charges. So let's say this is chlorpromazine, which definitely not because I didn't draw all the functional groups. But just let's say, because I'm lazy, let's just say this is chlorpromazine. So remember, chlorpromazine has a CpZi index of 1. So now what happens if you have a secondary amine rather than a tertiary amine? Would you have a greater CpZi or less than 1 CpZi? Less than 1, because remember, secondary amines are less optimal. What if you have a quaternary amine? What would the CpZi be? 0, because it doesn't penetrate the blood-brain barrier. Remember the try saying that way, right? The blood-brain barrier requires lipophilic compounds. Adding a positive charge or any sort of charge in it makes it a hydrophilic, not a lipophilic compound, so it can't penetrate the blood-brain barrier and get to the receptors. So it has a CpZi of 1. Illustrating the concept that tertiary amines are optimal, secondary are less optimal, very least optimal are your quaternary amines. Another thing I wrote here. So I said over here that your amines, your secondary over here. Your secondary amines are less optimal than your tertiary amines, but your tertiary amines are equally optimal to piperidine rings. So let's see. Put this in the cloud. Gotta love the cloud. Gotta love the cloud. Okay. Hopefully it's not too much of a mess for you. I'll see after when I do the review. Let's see. Okay, so here's your tertiary amine, your piperidine ring. Everything else being equal, so the scaffold and the 3-carbon chain are all equal. You're only changing the 3-carbon amine and the piperidine ring. So, okay, I said earlier that over here, in your amines, your tertiary amine is equipotent to your piperidine ring, or equally active to piperidine ring. So, if your CpZi of this tertiary amine is 1, what would the CpZi of this piperidine ring be? 1. Remember that tertiary amines and piperidine rings are equipotent, or equally active. Also, I said over here, okay, continuing with this amine concept. What if I have a piperazine ring? What would the CpZi of a piperazine ring be compared to a piperidine ring? More than 1. Okay, so let's see. So if I'm just gonna draw a blob because I'm too lazy. Okay, so 1, 2, 3, 3-carbon chain, and here's your piperazine ring. At the end, 2, 3. So your CpZi of this piperazine ring, since piperazines are more potent than piperidine rings, your CpZi would be greater than 1. Does make sense? Let me know. Hopefully, it's pretty straightforward. So, your tertiary amines and your piperidine rings are equipotent, leading to equal CpZi values. However, piperazine rings are more potent than piperidine rings, leading to CpZi values greater than 1. Okay, so now we know SAR. Let's do some more examples that he has. Gotta love examples. Okay. Okay, so let's say this one on the left has a CpZi value of 4. This is the piperazine ring. Everything being equal except changing this chlorine to a CF3, what would you expect the CpZi value to be? Greater than 4. why. Remember, I said earlier that, let's see, at this 2 position, you need an electron withdrawing group to make them potent. This is the same group we're talking about over here, down yonder. Down here. This is also the 2 position. So, remember that increasing electron withdrawing capacity increases the potency. So, remember knockoff Burkle? CF3 is more electron withdrawing than chlorine, leading to more potency at the 2 position. Therefore, your CpZi value should be greater than 4. Should be greater than at least this one over here. Okay, so another concept he talked about was for piperazine analog derivatives. For piperazine derivatives, adding a hydroxyethyl group increases potency. So to illustrate, let me box that, make sure you know that. Box it out. Okay, so let's see. Okay, so let's look at. So I said earlier that for piperazine derivatives, adding a hydroxyethyl group increases potency. Okay, so what a hydroxyethyl group is this group right here. It's called a hydroxyethyl because you have your hydroxy group and your ethyl group. Ethyls are 2 carbons, carbon 1, carbon 2. Here's your hydroxyethyl group. Okay, so would you expect this to be more... Let's see, comparing... Okay, so comparing this group right here, this molecule right here, to this molecule right here... Sorry, it's small. Would you expect the bottom molecule to be more potent or less potent than the top molecule? And why? More potent because of the hydroxyethyl group. So, if it's more potent, would you expect the CpZi value to be greater than, less than, or equal to 4? Greater than 4. Matter of fact. CpZi value... CpZi equals 10. Okay, so let's compare all these piperazine analogs to 10. CpZi of 10. Okay, so let's start over... going down. Okay, so everything else being equal, you have the piperazine analog with your piperazine derivative with your hydroxyethyl group. The only thing that changes is your chlorine over here to your CF3 over here. Would you expect the bottom to be more potent or less potent than the top one? If so, how big would you or how small would you expect the CpZi value to be? Put it in a cloud when you think. Okay, so since knockoff Burkle CF3 is more electron withdrawing than Cl, you expect this to be more potent. Therefore, your CpZi value for this would be greater than 10. Okay, so now the right two. Everything else being equal. Okay, I put this in the wrong place, my bad. Everything else being equal, you have, except you're changing the chlorine to a COCH3, and this one to a COC2H5. So this one has one more carbon than this one. Okay, so let's start with this upper right molecule first. Would you expect it to have a CpZi value of greater than, less than, or equal to 10? and why? CpZi is actually less than 10. Why? So even though it has oxygen, which makes an electron withdrawing, remember that carbons make things electron donating, so less electron withdrawing. So your CpZi is actually less than 10. Let me write that down for you. Carbons lead to more electron donating, less electron withdrawing, therefore lowering the CpZi. Okay. Tattoo that in your mind, or your right leg, or your left leg, or both. Let's see. So, if I said carbons are less electron withdrawing, therefore decreasing the CpZi, you would... Therefore, adding a carbon at position 2, where you need an electron withdrawing group, rather than a chlorine, would make it more electron donating and less electron withdrawing. Therefore, the CpZi would be less than 10. And adding more carbons to that position 2 doesn't really make a difference in terms of electron donating ability. So your CpZi is still less than 10. Actually, these are both, to be exact, these are both 5. So adding more carbons at position 2 doesn't really change the CpZi. They're still basically as potent. Okay, so now you have, final thing about your phenothiazines, is your long-acting repository piperazines. So, this is your piperazine, remember. So, backstory. So, problem with your piperazines is that a lot of them are dosed several times per day. So, using medicinal chemistry, which is why I love this, how can you change the molecule so that you can increase patient compliance by decreasing the daily dosing regimen? This is one of the reasons I love medchem. So you can actually create an ester. So, and remember, esters in vivo or at the cellular level, esters are hydrolyzed to hydroxyl groups. So here's your ester group. Upon hydrolysis, so these esters are lipophilic enough to be stored in fatty tissues, and upon fatty tissue degradation, they're slowly leached out over time. Now, to get them to be active drugs, the cells hydrolyze this ester part into a hydroxyl part, leaving this same general structure, but you change this group to be hydroxyl group. So, this one is actually active, and this is actually not active. So, this increases patient compliance because as these ester molecules are leached out over time, slowly over time, they're hydrolyzed. So, instead of dosing everything like 4 times a day, you dose it once a day, and as these drugs are hydrolyzed, they become active. And you still have more stored in tissue, and they're slowly being leached out over time. So, now you see one reason I love medchem. It's pretty cool. Okay, so let's see. Here's metabolism. There's 5 different ways you can metabolize phenothiazines. Number 1 is dealkylation. So, And dealkylation means you're basically removing an alkyl group or a meth or any carbon group. So here's your alkyl group at the bottom. I drew these out for you so you know what they look like instead of just his abbreviations on paper. In case you might have to draw metabolites on exam. So here's your tertiary amine. You're going to dealkylate it, remove a methyl group to make it a secondary amine. You're going to dealkylate that or remove a methyl group to make it a primary amine. So these metabolites are termed NOR1 for the secondary amine and NOR2 for the primary amine. Next up, you can oxidate phenothiazine at the sulfur. So here's your sulfur at the top. You can oxidize it to a sulfoxide, which has 1 oxygen, which can be further oxidized to a sulfone, which has 2 oxygens. So no oxygens turns into 1 oxygen, turns into 2 oxygens. Note that both oxygens are double bonded to sulfur. And you can, number 3, you can form N oxides. So tertiary amines form tertiary N oxides. Secondary amines form secondary N oxides. Primary amines form primary N oxides. Remember, you keep the number of substituents on your nitrogen. So nitrogen has 3 substituents. 1, 2, 3. 1, 2, 3. All you're doing is just adding an oxygen. So secondary amines have 2 substituents, just add an oxygen. Primary amines have 1 substituent, just add an oxygen. Your tertiary amines are more stable. Your tertiary amine oxides are more stable compared to your secondary amine N oxides and your primary amine N oxides. Oh, forgot to label that. Primary N oxide. So your tertiary amine oxides are your most stable of your N oxides. Number 4, aromatic or para-hydroxylation. You can hydroxylate the phenothiazine at either the 7 position over here or the 3 position over here. So hydroxylation means you're just adding a hydroxyl group. Add a hydroxyl group at the 7 position over here, which is the major product. The minor product is hydroxylation or addition of hydroxy group over here at the 3 position, which is the minor product. Finally, number 5, you can glucuronidate a phenothiazine. Only if you have an OH. So, if you have the OH, you can glucuronidate it. So here's your OH. You're just glucuronidating it, replacing it with a glucuronide group. Finally, a big concept: metabolites are less active compared to their parent, or they're either inactive or less active than their parent. Okay, so now we're going to talk about your thioxanthines. So your thioxanthines are basically your phenothiazines, except they result in a isosteric replacement of nitrogen with an sp2 hybridized carbon. In English, what that means is, here's your phenothiazine. Ooh, prototype, which one is it? Prop quiz, which one is it? I just give you the answer. It's chlorpromazine. Here's chlorpromazine. To get the thioxanthine equivalent of it, you're going to replace this nitrogen with a sp2 hybridized carbon. Same chain length, 3 carbons here, same tertiary amine. Literally all you're doing is replacing this nitrogen with a double bonded carbon, or an sp2 hybridized carbon. These are equally potent with their corresponding phenothiazine. So if he gives you any phenothiazine, to draw the corresponding thioxanthine, you have the same substitutions: chlorine over here, sulfur over here, same carbon length, and your same nitrogen, same tertiary nitrogen, or whatever he gives you, secondary or primary. The only thing you're changing is this double bond, and replacing the nitrogen with a carbon, making a double bond. So if I say that equally potent, if chlorpromazine has a CpZi of 1, what would you expect the CpZi of this molecule be? which is actually chlorprothiazine. 1. Remember, they're equally potent to their corresponding phenothiazines. So you have to make sure they're corresponding. The only thing you're changing is this nitrogen to a carbon and making this a double bond. Everything has to be the same. SAR is the same as your phenothiazines, except reducing this carbon double bond to a carbon single bond results in less activity because you need the electrons in that double bond for binding. Also, your thiazanthines have two isomers, your Z isomer or your alpha isomer, and your E isomer or your beta isomer. Your alpha isomer is more potent than your beta isomer. Therefore, would your alpha CpZi be greater than, less than, or equal to your beta CpZi? You're greater than. Oh, so next class of drugs we're going to talk about are your 676 tricyclics. So they're termed 676 tricyclics because you have a 6-membered ring, 7-membered ring, and your 6-membered ring. X and Y can be nitrogen, oxygen, sulfur, sp2 hybridized carbon, or an sp3 hybridized carbon. Basically, C single bonded to anything, especially a carbon. The ring system here is just scaffolding for attachment of their receptor binding groups. So basically, your composition and orientation of the ring system is important, meaning that you can put any atom in this ring inside the ring. So X and Y can be pretty much anything, and the ring. This ring can be up here. This ring can be up here. Literally, it just serves as a building blueprint or a building scaffold to attach other groups like a fluorine, chlorine, hydroxyl, methyl, ethyl. Basically, it just serves to hold other groups so that these groups can bind to the receptor. So that's why, and then X and Y can be any of these groups. Here is the phenothiazine 2 position. Probably unimportant, but he just talked about it. So, when looking at these 676 tricyclics, they follow the same basic SAR or receptor binding structures that the phenothiazines and your thiazanthines do. For example, you have your sp2 hybridized carbon there. You have your 3 atom chain. You have your basic tertiary amine. Remember, basic meaning N does not have a positive charge. Your electron withdrawing group. It's awkward. I thought I drew it. Here you go. There's your chlorine. Your electron withdrawing group at the 2 position. No, that's why I said 2 position, because that is a 2 position. Electron withdrawing group. And then... Yep, okay. Same basic requirements. So basically, I'm pulling from the SAR of your phenothiazines. Please refer back earlier to the video if you're confused about what that is, since I just explained it. I'm not going to explain it again. Don't have time for that right now. Let's see, ain't nobody got time for that. Okay, so, trick question. Does this follow the same SAR as your phenothiazines? I'm referring to this molecule right here. Also, these should be in clouds. I'm just gonna put a cloud above it. Okay. Okay, so does it or does it not? Yes, it does. So I'll go through the easy parts first. Here's your sp2 hybridized carbon. Tertiary amine, basic tertiary amine. Remember, basic can't have a positive charge. What else? can or cannot have an electron withdrawing group right there. Doesn't matter. Okay, so the hard part is you may or may not have thought it does follow the SAR because you thought this nitrogen was a terminal nitrogen. In fact, remember that I said that a 3-atom chain is necessary. Not necessarily carbon chain, but a 3-atom chain. So here's atom 1, atom 2, atom 3. So it still follows that 3-atom chain. It's not just all carbons. So be sure to look for your terminal amine, your amine at the end, when assigning which one's the basic amine. Got it? Get it? Hopefully, good. Okay, so one concept Dr. Glenn introduced is the question of why do piperazines and hydroxyethylpiperazines, why do piperazines bind better, or why are they more potent than your traditional phenothiazines or even some of your atypicals like your clozapine-like compounds? So, here is your receptor in here. This is your receptor. You have an aromatic binding site, an electron acceptor site, an amine site, and your auxiliary electron acceptor site. So notice how and let's look at your phenothiazines first. So this is your phenothiazine. So your phenothiazine, here's your ring. The aromatic part binds the aromatic binding site. Ooh, this is bothering me. This thing is number one. So your nitrogen binds the electron acceptor site, and then your basic tertiary amine binds your amine site, with nothing binding to the auxiliary electron acceptor site. However, your piperazine and your hydroxyethylpiperazines, they do bind to your auxiliary binding site. So here's your aromatic binding site. Your nitrogen binds to the electron acceptor site. This basic tertiary amine binds to your amine site. And your piperazine ring is long enough so that it binds to the auxiliary electron receptor site. Whereas your phenothiazines aren't long enough to bind to this auxiliary site. And more binding leads to more potency. Your clozapine-like compounds, basically some of your atypicals that look like clozapine or look like clozapine, have the same problem that phenothiazines do. They bind to the aromatic binding site, electron acceptor site, the amine site. However, they're not long enough to bind to the auxiliary electron acceptor site. So, why is this 3-atom chain important then? So this 3-atom chain is important so that the molecule can reach that amine binding site. So you have to have the amine binding. You have to have the 3-atom chain, not necessarily carbon, but 3-atom chain, in order for the molecule to reach the amine binding site, and have greater potency as an antipsychotic. Okay. So the atypicals, antipsychotics, they can have the same SAR as the phenothiazines, but not necessarily. And he just wanted to show these structures to illustrate that concept. So remember, you have to have your basic tertiary amine. Basic, because it has no positive charge. Tertiary amine, because it's a tertiary amine. I hope you know what that means by now. If you don't, please watch the beginning of the video. They might have skipped. Let's see. You have your 3-atom chain, not necessarily carbon, but 3-atom chain, all the way to your basic tertiary amine. So you have atom 1, atom 2, atom 3. Let's see. And remember that your atom 1 always is the first atom coming out of the ring system. You have your sp2 hybridized carbon, and that's pretty much it. So they can have the same SAR as your phenothiazines, which can lead to them binding to the same receptors and having the same antipsychotic effects. They just don't follow most of the SAR of the phenothiazines. Okay, so almost done with your drug classes. So these are your butyrophenones. These are butyrophenones. These are one of the most potent antipsychotics, but they also produce the most EPS, extrapyramidal. Say that 3 times fast. Extrapyramidal stimulation. Your prototype is haloperidol, shown below. I'll give you the important features after I go over the general structure of your butyrophenones. So your butyrophenones look like this. Either this one or this one. I'll explain the difference soon. So you have your aromatic ring with the Z group attached. Usually the Z group is fluorine, which you see in haloperidol. sp2 hybridized carbon, 3 atom chain, N equals 3. sp2 hybridized carbon, basic tertiary amine, just like your phenothiazines. Wow, if you know your phenothiazines, you basically know everything. And then your piperidines, or everything stays the same, you have a piperazine. So the only thing that changes is either your piperidine at your basic tertiary amine or your piperazine at your basic tertiary amine. This is your butyrophenone part. Same thing, your Z group, which is usually your F, sp2 hybridized carbon, 3 atom chain, your basic tertiary amine. Remember, your 3 atom chain goes all the way to your basic tertiary amine. So 1, 2, 3, 1, 2, 3. Here's your basic tertiary amine. Your R1, your R2 groups, R1, R2, R1, R2 can be heteroatoms, not usually nitrogen or oxygen, and sp2 hybridized carbons. So in the haloperidol example, you have your fluorine, like I said, your sp2 hybridized carbon, 3 atom chain, 1, 2, 3. Your basic tertiary amine right after your 3 atom chain. And let's see what else is there. There's one more thing. Here's your heteroatom. Here's your heteroatom, which is oxygen, and then your sp2 hybridized carbon over here, attached over here. For this molecule, you have your fluorine as your Z group, your sp2 hybridized carbon, your N equals 3 chain length, your basic tertiary amine, your heteroatom, and your sp2 hybridized carbon here. So diphenylbutylpiperidines are basically butyrophenones, except you replace the carbon oxygen with the parafluorophenyl ring. In English, what that means is if you look at your typical butyrophenone, which is up above over here, you're literally keeping the same structure, except the only thing you're changing is this group right here to a phenyl ring with a fluorine at top. So carbon double bond changes to a phenyl ring with a fluorine at top, everything staying the same. These are typically less potent than your corresponding butyrophenones. Okay, so I summarized everything in the last page of our handout for the exam in a few typed pages because I don't feel like writing anymore and I'm tired. Also, we don't know it. Also, we talked to, shout out to Chad, she talked to Glennon, and she said we don't need to know any of the structures on this last page of the handout for this exam, the one about titled Antipsychotic Agents, Mechanism of Action. So any newer agents, don't have to memorize the structures for those, just know their names and their mechanisms of actions. So I'll go through this whole last page in type form. Okay, so how do we know that dopamine is the one responsible for psychosis? Okay, number 1. Amphetamine, the amphetamine cocaine hypothesis. So amphetamines are indirect. You can just follow along. I'm going straight down. Amphetamines are indirect dopamine agonists that cause dopamine release from presynaptic neurons by reversing the DAT, or the dopamine transporter. Chronic high doses of amphetamine can cause acute paranoid psychosis. Likewise, cocaine is a dopamine reuptake inhibitor. Chronic high doses of cocaine can cause acute paranoid psychosis. Ooh, pop quiz. So, which one should you take first if you want to take them both? Amphetamine or cocaine? Amphetamine before cocaine. A, B, C. Why? Because you're releasing dopamine from the neuron, and then you're preventing, using amphetamine, then you're preventing its reuptake to the you're preventing its reuptake by cocaine. So you're leaving more dopamine in the synapse, leaving it more available to bind, and you get high better. Not advising that you should do it. I'm just giving you the science behind it. Please don't do it. One at a time, please. Okay. So, EPS. So, Parkinson's is caused by degeneration of Ooh, what the? Dopamine. So, Parkinson's is caused by the degeneration of dopamine neurons, leading to increased. Awkward. Okay, that should say decreased dopamine and increased acetylcholine. So degeneration of dopamine neurons leads to decreased dopamine and increased acetylcholine. These two are inversely related, increasing one decreases the other, like a seesaw. Parkinson's, therefore, is treated with dopamine agonists to increase the dopamine. Biosynthetic cursors like L-DOPA, which is converted to dopamine. Dopamine-releasing agents, therefore increasing dopamine. And anticholinergics. Because, as I said earlier, these two are inversely related. So decreasing acetylcholine increases dopamine. EPS, extrapyramidal stimulation, is a side effect of the antipsychotics and is caused by blockade of dopamine receptors related to movement, and particularly in the corpus striatum. So these structures I'm referring to are in the handout he gave us. I just screenshotted it. So the corpus striatum is responsible for muscle coordination movement via dopamine. The limbic system and the cerebral cortex are responsible for emotion, perception, and thought, and other pathways are via dopamine, and other pathways via dopamine are responsible for hormone secretion and sexual behavior. And dopamine is primarily stimulated by the midbrain. And where was I? Okay, so EPS, a side effect of antipsychotics, is caused by blockade of dopamine receptors related to movement, mediated by corpus striatum. Therefore, let's see. It can be said that antipsychotics produce Parkinson's-like symptoms. Since antipsychotics produce EPS, which is caused by a decrease in dopamine, and Parkinson's is caused by a decrease in dopamine, it can be said that antipsychotics, therefore, produce Parkinson's-like symptoms. Therefore, EPS symptoms are treated with anticholinergics. You can't really treat with dopamine because antipsychotics are already blocking the dopamine receptors. So it doesn't make sense to treat them with dopamine, therefore you treat them with anticholinergics. Remember, anticholinergics decrease acetylcholine, therefore increasing dopamine. Additionally, psychotic and schizophrenic patients experience high levels of dopamine, so you can't treat them with dopamine agonists, which decrease dopamine. Treat them with anticholinergics, and selectively target the limbic system and cerebral cortex. In psychotic and schizophrenic patients, they have an increase in dopamine, primarily found in the limbic system and the cerebral cortex. So you want to selectively target this without inhibiting their muscle coordination or movement or the sexual behavior or hormone secretion via anticholinergics. Number 3, dopamine agonists like L-DOPA, which is a precursor to dopamine. And dopamine. Wow, I made a lot of mistakes in this. I should have checked it. And apomorphine. Oh, no, just kidding. Okay, so let's see. Dopamine agonists like L-DOPA, which is a precursor to dopamine. Also, apomorphine, which is a dopamine receptor agonist, can produce exacerbated psychotic symptoms. So increasing dopamine through receptor agonists or dopamine itself can produce psychotic symptoms. Number 4, increasing the affinity of an antipsychotic to the dopamine receptor increases its potency. It's a linear relationship. So increasing the binding of the antipsychotic can increase its potency or decrease the dose needed in a linear fashion. The common structural features of antipsychotics that allow them to bind to the dopamine receptor include the aromatic. This is all from the Phenothiazines SAR. So you should know this by now. The aromatic ring, the sp2 hybridized carbon, and the basic tertiary amine, which is 5.5 angstroms away from the aromatic ring. Remember I showed you the picture of the receptor and the auxiliary binding site? So you need the 3-atom chain so you can reach that amine binding site. Remember that. Dopamine binds to the aspartate residue in transmembrane 3 and to amino acid residues in transmembrane 5. Remember, the dopamine receptor is a GPCR. GPCRs are 7 transmembrane receptors. 1, 2, 3, 4, 5, 6, 7. So dopamine binds 2, 3, 4, 5, 6, 7. So dopamine binds at this receptor, transmembrane 3, and also at this receptor, transmembrane 5. Likewise, antagonists work by binding to these same receptors. This is why antagonists work, because they bind at the same receptors and block dopamine. So, antagonists also bind to transmembrane 3, but also transmembrane 6, transmembrane 7, which I wrote over here. If antagonists occupy the site, dopamine can't bind, just like what I said. Next. Whoa, I went through that fast. Okay. Here are the other potential mechanisms that Glennon talked about. Importantly, your dones belong to 5-HT2DA receptor antagonist category, your SDAs. Risperidone, which is your prototype. Don't have to know the structure though. Lurasidone, ziprasidone. Ooh, pop quiz. Brand name for ziprasidone. Geodon. Paliperidone, which is the active metabolite of risperidone. Namely the 9-hydroxyl form, and Haloperidol, which is also potent at the 5-HT3 and 5-HT6 receptors. I'm going through this fast because it's pretty self-explanatory. Not really much chemistry, just a lot of biology and words. 5-HT6, 5-HT7, their mechanism is not understood. 5-HT3 might represent a novel mechanism, TBA. Glutamate receptors, mGlu2, 5-HT2A receptor heterodimers. So basically, what that means is here's your mGlu2 receptor, and here's your 5-HT2A receptor. These can dimerize or combine to produce basically one functioning receptor. So mGlu2 agonists can potentiate the action of certain 5-HT2A receptor antagonists. So attaching an mGlu2 agonist to a 5-HT2A receptor antagonist can increase the effect of an antipsychotic to produce a more potent antipsychotic. Important stuff about your dones, like risperidone, ziprasidone. They don't require an aromatic fluorine. They're Lorazepam and risperidone are L caps. Ooh, review. What are L caps? Abbreviation. They are your long chain aryl. Piperazines. L caps. I swear I know this. Okay. Long chain aryl piperazines. Please refer to the previous video on long chain aryl piperazines. Probably near the end. Yeah. Lorazepam and ziprasidone contain piperazine ring and a sulfur instead of oxygen. Laz and risperidone. Risperidone has an oxygen. Lorazepam and ziprasidone have sulfurs. Finally, these drugs are the novel therapeutic agents. Here's the drug mechanism. I'll talk about it in case you're an auditory learner. Amphetamine is a D2 dopamine and 5-HT2A antagonist. Remember, ooh, I think I just glossed over that. Hold on, let me go back. No, definitely didn't. Okay, so remember the dopamine 1 family not directly involved in psychosis. Directly, but your dopamine 2 family is involved in psychosis, which is why you have antagonists at that receptor family, the D2 family. So Amphetamine is a D2 serotonin 2A antagonist, which is also potent at 2-HT2A and receptors and at D1 through D4 receptors. Aripiprazole is a D2 partial agonist when dopamine is low, but it functions as an antagonist when dopamine is high. It's also known as a dopamine stabilizer because it acts when dopamine is low and differently when dopamine is high. Aripiprazole Laroxyl is a long-acting repository form of aripiprazole that works by cellular hydrolysis of the lauric acid group. Remember, referring back to our earlier in the video, the long-acting repository piperazines, which have that ester group that are hydrolyzed to form the long-acting form, so for increased patient compliance. This also works by hydrolysis, but through a different group, the lauric acid group. So ester groups are hydrolyzed to OH. Brexpiprazole is an SDAM. Like, damn, we got an exam on Friday. SDAM, which is your serotonin dopamine activity modulator. It's a D2 partial agonist. Cariprazine is a D2 and D3 partial agonist. And pimavanserin is your 5-HT2A or serotonin inverse agonist. Emphasis on the inverse. Okay, so now to review. Your tricyclics composed of 6-member ring, 6 or 7-member ring, or 6-member ring. Anything less than 6 or greater than 7 leads to an inactive ring. First class of tricyclics are phenothiazines. Prototype is chloropropyrazine. Chloropropyrazine index, or CPZI, measures the potency of a drug relative to chloropropyrazine. Anything greater than 1 is more potent, less than 1 is less potent. Your SAR. Sulfur is optimal at the X. At Y, N or sp2 hybridized carbon is optimal. At the 2 position, you should have an electron withdrawing group. 3 position, H, hydrogen or an electron withdrawing group. Must have a tertiary amine that's unbranched. Piperazines are more potent than piperidines, which are equipotent to tertiary amines, which are more potent than secondary amines. Your ring system is not planar but V-shaped. Planarity or a 5-member ring leads to no activity in the middle. Make sure you have a 3-atom side chain, not necessarily a 3-carbon, but a 3-atom side chain. Branching, shortening can unmask the antihistaminic or anticholinergic side effects. Because remember, your antihistamines look just like your prepared phenothiazines, except this is a 2-atom chain rather than a 3-atom chain. So you have decreased antipsychotic activity with shorter chains, longer chains, or branch side chains. Let's see. Remember, you have to have a tertiary amine, because quaternary amines or charged amines cannot penetrate the blood-brain barrier. You have to have a tertiary or less amine. Anything without a positive charge. For piperazine derivatives, adding a hydroxyethyl group increases potency. Remember that a hydroxyethyl group is just a hydroxy group with an ethyl. hence hydroxyethyl. So ethyl is 2 carbons, 1, 2, from the basic tertiary amine. So from the basic tertiary amine, you have a hydroxyethyl group. 1 carbon, 2, hydroxy group. Increasing number of carbons at your 2 position increases the electron donating ability, therefore decreasing the electron withdrawing ability, and therefore decreasing your CpZi, making it less than 1. Your long-acting repository piperazines, good for patient compliance. They worked by hydrolyzing cellularly at the cellular level the ester over here to a hydroxyl over here. Because esters are stored in fat, and as fats are degraded in the body, these are released, and as these are released in the body, they hydrolyze to the active form, which is the hydroxyl form. 3 ways, 5 ways, a lot of ways that prepared phenothiazines can be metabolized. N-dealkylation, oxidation, and oxides, aromatic parahydroxylation, and glucuronidation of the hydroxyl group. Remember that tertiary thiazanthes, remember, are basically your prochlorperazines, except you're changing this N to a double bond. Equally potent to the corresponding phenothiazines. SAR is the same as phenothiazines, but if you reduce the C double bond C to a C double bond C single bond C, you will get the reduced activity. You have 2 isomers, your Z and your E. Your Z isomer is more potent than your E isomer. Your 676 tricyclics, X and Y, can be any of the following: nitrogen, oxygen, sulfur, sp2 hybridized carbon, sp3 hybridized carbon, which is a C single bond C. Ring system is just scaffolding. Follows the same SAR pretty much as your phenothiazines. You got your sp2 hybridized carbon, your 3 atom chain, electron withdrawing group, and your basic tertiary amine. Blah, blah, blah. Remember, your piperazine, your hydroxyethyl piperazines are a lot more potent because they can bind to the auxiliary binding site. Whereas the other ones don't have the extra binding, therefore are less potent. Your atypicals pretty much have the same SARs, can have the same SARs as your phenothiazines. Butyrphenos are your most potent. Your prototype's haloperidol. Your general structure contains fluorine, sp2 hybridized carbon, 3 atom chain, basic tertiary amine, and this can be a piperazine or piperazine. Your R1 and R2 groups can be heteroatoms, nitrogen and oxygen, and an sp2 hybridized carbon. Your diphenyl butyl piperazines are basically butyrophenones, except you're replacing that carbon double bond oxygen with a carbon phenyl fluorine at top. They're typically less potent. They're corresponding butyrophenones. Hopefully this is self-explanatory. If not, let me know. Yeah, hopefully these are self-explanatory. Just memorize them. No structures. No SARs. Finally, if you have any feedback, thanks for watching. Hope you enjoyed that. I didn't. Actually, I did. I love him again. If you have any kind of comments, feedback, please feel free to leave it at polevChristianRui629. Also, feel free to subscribe to this YouTube channel. I think you get updates every time I upload a video. I try to do it at least 2 days before the exam, if not more. Also, feel free to check the YouTube description below this video for the link to download this video and the associated handout, and to also follow the poll EV in case you don't want to, type it out. Just click on the link. Thanks for watching and good luck with the exam.